Hi, Algebra 2 students. We are jumping right into day 6. So when you have a function that can be like broken up into multiple little lines or shapes, that's typically called a piecewise function. And so we're going to be looking at piecewise linear functions, just meaning all of the parts are lines themselves, right? So for the first one, it's saying, can we sketch this guy and then be able to, can we come up with the values and then be able to graph it over here? So there's a couple things that you want to be able to keep in mind, right? On the graph, when we have these set domains, it typically means we have endpoints. So if you have an endpoint that is greater than or equal to or less than or equal to, that means it needs to be a closed circle. So like closed up like this. Whereas if it's strictly greater than or strictly less than, that means it's going to be an open circle. And so it would look like that, meaning you're not including that value. So there's the first little reminder. Having your calculator nearby is helpful because you have an option. When you want to go fill these in, you can type them into Y1 or you can do a little mental math, all right? Depends where you're feeling at the moment. If you'd rather just go into Y1, feel free. So you could go X minus 3 and you can take a look. And then if I go look at the table of values, I would want to look specifically, that one's saying from -3 to 0. So I can zoom in a touch here. So at -3, it comes out -6. At -2, it's -5. At -1, it's -4. But now here you're going to note up top, it's saying that we go to 0, but we don't include it. So I'm going to still want to plot at 0. I'm just going to plot it as an open circle. So to kind of account for that, I'm going to split this in half. And at 0 on this particular one, it's at -3. Right? So that little -3, I'm going to have an open circle. All right. Then to do the rest of the chart, I can go back into my calculator and I can change it up. So now I've got 1/2 x and then +4. All right. And now I can go right back to my table and I'm going to start at 0. So at 0, it's starting at 4. And then I can copy from there. So then 1, 2, 3, and 4, let me slide this over so that I can write. Maybe I can squeeze it. There we go. All right, at 1, it's 4.5. At 2, it's 5. And at 3, it is 5.5. And finally, 4, it's 6. Okay, so now we've got our points that we're going to plot. So when you learned to graph these piecewise, you might have learned to graph the whole line and then erase the parts you don't need. We're taking a more direct approach of saying, let's plan ahead and then we'll only plot the points that we need. So the first line from -3, so -1, 2, 3, and then down to -4, -6. And my eyes jump if I don't label things. So do it if you need to. If not, then you know your scaling should just be 1s on the X and 1s on the Y. All right, so at 0, -3, we have an open circle. Make sure that it is clear that you can see that. And I know that this graph copied pretty dark, so you might have to like exaggerate that open circle a little bit. All right, so connect the dots. We're looking at this. Griffin, do you need something? No? All right. Never know what's going on out there. All right. And the other half of the line at 0, we start up at 4. So let's see, we've got 2, 4. And now because of this is a closed circle here. All right. So we close the circle there. And then at 1, we just go up to 4.5. At 2, we're at 5 and so on. So we're going to have another closed circle right there. All right. At 4, 6. All right, connect the dots. So you get this little line segment up top. You get a little line segment below. All right. So that's what our graph should look like. Right? Then it's going to say down here, state the domain and range based on what you came up with. All right. So state the domain. So remember, domain from left to right. What we'd want to look at is this first little segment goes from -3 up to 0, and it includes -3, but it doesn't include 0, all right? But we also have that other piece up top. We have this piece that starts at 0, and it goes up to 4. So we could say in union with, it includes 0 all the way up to 4. Right? And now, while this isn't wrong, If I'm saying it starts at -3 and goes to 0, not including it, but oh, just kidding, it does include it and keeps going, what I really mean is I can more concisely write this, that the domain just goes from -3 to 4, including all of those values. So that would be the domain of the graph. So even though there's that little jump, there's not a break in the x's. All the x values exist between -3 and 4. The range, on the other hand, when I think we're going to write from bottom to top, right? What we have in that case, we'll look at the lowest point on your graph. If I slide back up so we can see, the lowest point right here is -6, and then all those values are filled in until I get to -3. So this first little part of the range goes from -6 up to -3, but it doesn't include -3, all right? And then we can say in union with, and now let's look at the other segment. So when I slide back up here, the lowest point here is 4, and then it goes up to the highest point, which is at 6. So then I can say in union with 4 up to 6. And since there is a big gap in between them, I can't join these and make this one set. I would simply leave it at these two things. So here is your domain, and then here is your range. And that can happen with piecewise functions, that you have just little pieces of the x's and y values that you have possible to be able to graph with. So when it says make a table and graph it on the axes, if a table's not provided like the last one, then just give yourself, a little t-chart or a little table that you can do. All right. So what I would suggest is probably making two separate tables. I mean, it's okay if you make the same one, but it's never a bad idea to treat the first function and then give yourself a table for that. And then take the second function, and you might have more than two functions even. So however many tables you need is perfectly fine. All right, they don't have to be super fancy. So pay attention to the domain that you're given over here. For the first one, we want values less than 2. So we might want to plug in, -1, 0, 1, and 2. So even though it strictly says less than, just remind yourself this is going to be then an open circle here, but I still want to plot that point. And then for the second part, this is going to be for all the values greater than or equal to 2. So maybe start at 2 and then go 3, 4, 5, something like that. And in this one, this is going to be a closed circle. I do think it's important to note that even if you literally draw a closed circle or an open circle next to it, as long as you know what you're talking about, it's a good reminder there. Otherwise, it's easy to forget those details. All right? So again, you can do a little work algebraically on your own. You can plug it into the calculator and let the calculator do the work. It matters not to me. Just do what works best for you. All right? So if I go into my y equals and I type in 5 minus x, I'm just going to that table of values and just recording the couple values that I care about. So just be careful because on the calculator, it writes it in the reverse order sometimes, depending on how you wrote it down. So at -1, I've got 6. At 0, I've got 5. At 1, I have 4. And at 2, I've got 3. All right. So we can plot those points over here. So same thing. Just count carefully so that you can see what's happening on your graph. So at -1, we've got 1, 2, 3, 4, 5, 6. All right. At 0, we are up at 5. 1, we were at 4. And at 2, we are at 3 with an open circle. All right. Please use a straight edge whenever possible so that we make this as nice and neat as we can. Mm-hmm. I always say it, but I don't do it. You should also use pencil. Just saying. All right, over here for the second piece of it, you can go to the calculator. Another option, if you do have a pencil, I think I mentioned it in the first video, is the fact that if you learned it as here's, y equals mx plus b, and you could graph the whole thing and then just erase the part that you want, you could do it that way. So you could come up here to 2 and then say I'm going up 1 and right 2 and up 1 and right 2, and then just only connect it for the spots you want. So just know that that's an option. If you're afraid that that will confuse you, then you're going back to your calculator and you're just going to look up the table of values here. All right. So then starting at 2, that comes out as 3. At 3, it's 3.5. 4 is 4. 5 is 4.5, and so on. All right. So just as long as their value is bigger than 2, you don't have to plot every single one of them. But something you'll notice immediately, 2, 3 starts as a closed circle. It's actually going to close in the circle that we left open, right? And then I'm just going to come over to 4 and plot 4, and then 6 would be 5 and so on. All right. So it kind of looks like a funky absolute value graph in that it's not perfectly symmetrical once it's a little slanted, all right? Which is why it has to be done with a piecewise. You couldn't be done with just one single function here. All right. It says determine the y-intercept of the function algebraically. What can a function, or y, excuse me, can a function only have one y-intercept? All right. Well, if we calculate it, excuse me, algebraically, then we'd be taking and plugging in x equals 0. Right? In that case, you have to plug it in where x equals 0 is part of the domain. So when you look up top, 0 falls into that first one. So if I plug in x equals 0 into this, I would get 5 minus 0, or just 5 all by itself. So that should be our y-intercept, the 0.05. And it is if I come back and look at the graph right there. All right. When it says y, can it only have one y-intercept? Well, if I had more than one y-intercept, it would fail the vertical line test. So for it to be a function, it has to pass the vertical line test. So I'm going to say it would fail the vertical line test if there was more than one y-intercept. All right. When it says find the x-intercepts of each individual linear equation. So x-intercept, that means we're going to set y equal to 0. All right, take the first one. If I set it equal to 0, and then the second one, if I set it equal to 0, okay, we can solve each. So this one's quick. Just add this over. X would come out to be 5 here. So that would be the 0.50. If I subtract 2, and then double both sides, this would be the point x equals, or excuse me, it'd be x equals -4, which would be the point -4, comma 0. Right? So that would be each linear function's x-intercept. When it says, why does your graph contradict the answers? Well, what we mean by that, if we look back at the graph, where does our graph hit the x-axis? Well, nowhere. Right? It doesn't cross it at all. So when it's saying, why does your graph contradict it, we can say our graph has no x-intercepts. Okay. When it's saying, how can you resolve the fact that the algebra seems to contradict your graphical evidence, right? Well, you would only have the x-intercepts if those particular x values were plotted, and they're not. We have restricted domains. So I'm going to say that the graph has a restricted domain. So we don't see the x-intercepts. And that's going to be true when it's literally called a piecewise function. You only see pieces of it. So it depends on which part of the line or the part of the graph that you see as to whether or not the x-intercept is there or not. All right. When we hop on over to the next page, we are going to specifically pass up number 2 because I love this one, but I think it's best to do in class together. So this first one, always uplifting topics. It's talking about Lyme disease, saying it's a bacterial infection transmitted to humans by ticks, which I actually pulled a tick off of my dog like a week ago, and it was giving me a heart attack. It says when an infected tick bites a human, the probability of transmission is a function of time, right? Since the tick attaches itself to the skin. So if you look over here on the x-axis, this is the time, and then the y-axis is the probability of infection, right? Or the probability that it would transfer that Lyme's disease, right? So when we read through it, we're going to be using the graph to fill in the blanks. So it says during the first blank hours, the probability is just 0. So if I start the first 24 hours right here, it stays 0, which that's actually a really good sign for us humans that if you catch it in the first 24 hours, you have 0 worries, right? No probability of having Lyme disease. During the next 3 24-hour periods, the rate of the change in probability is always positive. Remember, rate of change, all right, or average rate of change. That's talking about the slope. So the rate of change, it's increasing. You see those positive slopes there. But it's much greater for the middle period, going from a probability of 10% at the 48-hour mark to blank percent at the 72-hour mark. All right, so at 72 hours, I would say what, like 75%, something like that, right? And then ending at a probability of blank percent. So the last part right here, I don't know, I would say like maybe 98, 99, something like that. We can even go like approximately, right? And then saying after 96 hours, the probability is almost what? Well, after 96 hours, it's essentially 100%, like meaning it's going to be a guarantee, unfortunately, that you would end up with Lyme disease. So like I said, real uplifting. All right, identify the axes and the scales. Okay, so on the x-axis, that is representing time. Right? And when we're saying the scales, we're talking in hours. Right? The y-axis, that was the probability, all right, of the disease. And it's actually in a percentage out of 100. Right? So they're not calculating it, in terms of like numbers of people, it's the percentage of people, right? So when it says identify key intervals, well, there's no one way to answer this, but for me as a person, to me, the key interval that I would note from this is the fact that, all right, from the 48-hour to 72-hour, it's not a guarantee, but that is a huge risk that we're taking. So I think a key interval here would be the probability of disease transmission I'm going to be a little dramatic here, drastically increases from 48 to 72 hours. When you look at the last page, here we've got the incidence of measles. So unfortunately, you guys, when you use real data, some of it's like sad stuff. They don't really like make data charts of like rainbows and sunshine. So when it's saying actually, maybe they do. You never know. But from 1974 to 1980, there's a drastic fluctuation in the incidence of measles, in the United States. I want to take a look at, can we at least set it up? So let me come down here because the first question says, identify the axes and the scales. Okay. Well, anytime time is involved, that's almost always going to be your x-axis, your independent axis. So time down here. And then the vertical, the y, right? That's going to be the number of cases. But if you look carefully, it says per 100,000, right? So when they say 10 cases, they don't mean 10 cases total, 10 cases out of, each chunk of 100,000 people. So it's the number of cases per 100,000 people. All right. Now we can't identify the key intervals till we actually graph it. So let's see if we can figure out what's going on here. So when we kind of skim the question, actually, I don't even need to skim. Go right back to the first sentence. From 1974 to 1980, they talk about the fluctuations. So the time, the scaling on the x-axis is going to have to talk about the time from 1974 to 1980. So we can start at 1974. That's perfectly fine. All right. So then if we let each year, so 75, 76, 78, 80. All right. And then if we look at the cases, this is where you kind of have to skim the question. I'm going to come back up here for a second. I got a highlighter, so maybe I'll do a little highlighting here. It's saying, let's see, there's an increase from, I see 10 cases. It's going to hit 11 cases. Ooh, it reaches a maximum of 26 cases, and then it falls down to about 5 cases. So the reason I'm highlighting all those is I need to know like what numbers have to go on that y-axis. So it looks like as low as 5 and then as high as 26. So when you're picking your scaling over here, maybe we count by 5s and go 5, 10, 15, 20, 25, 30. That actually works pretty nicely. So we can start it at 0. oops, and then count from there. So you do have to think a little bit before you just start like slapping numbers down there. All right. Now let's see if we can read carefully. So as we go through it, it says in between 1974 and 1975, there was a slight increase in incidences from 10 cases per year of 200,000, or excuse me, per 100,000 up to 11 cases. All right. So in 1974, we're starting at 10 cases and then we're going up to 11 cases. So just like a smidge above that there. Okay. The next 2 years saw a substantial increase in incidence, and it reaches a max in 1977 of about 26 cases per 100,000. So in 1977, let's go up and plot that 26 cases. And then it says from 77 to 79, the incidence fell to 13 cases per 100,000 people to about 5 cases. All right, so the way I would interpret that when it says it fell to 13 and then to 5, I'm going to assume that 78 is the 13 cases. So kind of like halfway-ish there. And then in 79, all the way down to 5 cases. All right, and then finally, in 1979, the incidence stayed about the same to 79 to 80. All right, so once you plot all those, if you have a straight edge, great time to use it. We would want to connect with nice straight line segments in between all of those points that we plotted. All right. So yeah, do you maybe, if you're doing this independently, have to read through it carefully a couple times? Yes, you might, all right? And that's okay. But our graph should look a little something like that. When it says identify the key intervals, to me, again, not trying to be alarmist, but since it's talking about measles, and that's kind of a big deal, I would say when it was saying it saw a substantial increase in incidence, where it reached that max in 1977, I would say then where I would be concerned would be between 1975 and 1977 when we saw that big jump. Right? So the years 1975 to 1977, where the cases increased from, I think it was 11 per 100,000 to 26 per 100,000. Right? That would be a key interval. But what if we want to be a little happier about it? Another key interval you might be looking at is from 77 to 79. They got it back under control. Right? So key intervals, we could add that one there. I don't have a ton of room, but that's okay. All right. We sketched the graph already. All right. And then the last part, it says, the graph is horizontal from 79 to 80. What can you say about the rate of change? Well, remember, rate of change is just talking about the slope. And so the rate of change, if it ends up as a horizontal line, the slope is essentially 0 there. So anytime that you have a constant, that means that it's not changing at all, and therefore the slope is 0. So hopefully it makes sense, the comparison of those two things.